for a particle moving in a straight line, we say that average velocity is displacement upon time, and it's quite the same when we deal with motion in 2 and 3 dimensions. The only change we make in the formula is we use delta r, that is the displacement vector. So when you see this formula, you see that the direction of the average velocity should be the same as the direction of displacement vector delta r. And why should that be so? Simply because you are dividing a vector by a scalar. That just changes the magnitude of the vector, not the direction. Now, you can expand on this equation and write it as V average is equal to delta xi plus delta yj upon delta t, which equals delta x upon delta ti plus delta y upon delta tj. And not to forget that if the motion is in 3 dimensions, you just need to add delta zk as well. So as an example, if a particle has displacement of delta r equal to 10I plus 4j in 2 seconds, we can say that the average velocity during this displacement is V average is equal to 10I plus 4j divided by 2 seconds, which equals 5I plus 2j. Or if you want to be more precise, this can be written as 5 meters per second I plus 2 meters per second j. And this average velocity, a vector quantity, has a component of 5 meters per second along the x-axis and 2 meters per second along the y-axis. So every second, the body is getting displaced 5 meters along the x-axis and 2 meters along the y-axis if it maintains this as the average velocity. Now, when we talk about instantaneous velocity, v, it is the velocity of the particle at some instant of time as opposed to some measurable span of time, which we use when we calculate average velocity. And using calculus, we write it as, that is the instantaneous velocity, as v is equal to dx upon dt. So let us try to understand this a little deeper. And if you see the path this bug takes in the xy plane, and imagine this xy plane as the wall on which the bug is moving, the bug is moving to the right along the curve, and therefore you can say that the position vector is also moving along with it. Let us say the bug's position vector changes from r1 to r2, and the displacement due to this is delta r, and this happens in time delta t. Now we will use the same idea we used in the earlier lesson on instantaneous velocity for motion in a straight line. And in case you've not seen the video, I would suggest you watch that video as well, and I'll put the link in the description below. So if you want to find the bug's instantaneous velocity at time t1, we shrink the time interval delta t towards 0. And mark my words, I'm not saying it becomes 0. So when you do this, that is, you shrink it towards 0, you shrink delta t towards 0, a couple of things happen that are quite visible. One, the position vector r2 moves towards r1. That causes delta r to shrink or reduce in length towards 0. Number two, the direction of the average velocity, that is delta r upon delta t, starts approaching the direction of the tangent to the curve at t1. And three, when this happens, the average velocity starts approaching the instantaneous velocity v at t1. And when delta t is almost 0, the average velocity is called the instantaneous velocity at time t1. So again, whatever we've discussed so far would very much apply to motion in 3 dimension as well. So we can say v is equal to d upon dt of xi plus yj plus zk, which equals dx upon dt I plus dy upon dt j plus dz upon dt k. And then you can simplify this equation further by writing it as v is equal to vxi plus vyj plus vzk. And you can see the scalar components are vx is equal to dx upon dt, vy is equal to dy upon dt, and vz is equal to dz upon dt. So I would like you to remember three things really well. Number one, instantaneous velocity at any point is dr upon dt, where r is the position vector of the particle at any time t. Number two, this instantaneous velocity is v is equal to vxi plus vyj plus vzk. That is, it is composed of three components. And number three, the direction of instantaneous velocity is the same as the direction of the tangent at that point. So if the velocity vector of the bug at some time t is like this, you can see it is a tangent to its path at that point. And it has two vector components, one in y direction, that is vy, and the other is in the x direction, that is vx. And at first it might look confusing that how can the bug have velocity in two directions? But if you think a little deeper, you'll find that it's because of these two components that the bug is able to take this curved path. In fact, imagine the bug suddenly loses vector vy. Then what do you think will happen? Well, the bug will start moving in the x direction because that's the only vector component it will have, and it will become motion in a straight line. Likewise, if you were to remove vector vx, the bug will suddenly start moving in vertical direction because that's the only velocity vector it will have. So you see, when we have motion in 2 or 3 dimensions, the path or the curve the particle takes is because of the velocity vectors the particle has at various points in its path. And these velocity vectors combine to give a resultant velocity and therefore direction to the particle at various points. So recall the orange spider from the last lesson, that is climbing a wall, and we asked what is the spider's velocity at t equal to 15 seconds. So how we approach this problem is that we first find the x component of the velocity at t equal to 15 seconds. Then we find the y component of the velocity at 15 seconds. And then we combine them to get the resultant velocity at t equal to 15 seconds. So to find Vx, we differentiate x with respect to time. And what we get is Vx is equal to dx upon dt, which equals d upon dt of minus 0.31 t square plus 7.2 t plus 28, which equals minus 0.62 t plus 7.2. And at t equal to 15 seconds, we get Vx is equal to minus 2.1 meters per second. Then we go ahead and differentiate y with respect to t, that is Vy is equal to dy upon dt, which equals d upon dt of 0.22 t square minus 9.1 t plus 30, which equals 0.44 t minus 9.1. And at t equal to 15 seconds, what we get is Vy is equal to minus 2.5 meters per second. And then we combine these two vectors to get the resultant velocity as v is equal to minus 2.1 meters per second I plus minus 2.5 meters per second j. So this is the direction the spider is climbing at t equal to 15 seconds. And we can go ahead and find the magnitude of velocity also as v is equal to root of vx squared plus vy squared, which is equal to root of minus 2.1 squared plus minus 2.5 squared, which equals 3.33 meters per second. And the angle it makes with the plus x direction can be found as theta is equal to tan inverse of vy upon vx, which equals tan inverse minus 2.5 upon minus 2.1, which equals tan inverse 1.19, which equals minus 130 degrees. And you must observe that tan inverse of 1.19 can be 50 degrees as well, which you can reject because you can see visually that this is the vector direction and therefore the angle has to be minus 130 degrees. So you see, the idea of instantaneous velocity is very important in the study of motion in 2 and 3 dimensions. But if you really want to get good at projectile motion and circular motion, I would suggest you head over to this playlist. And like always, if you like the video, please do give it a thumbs up and see you in the next video.